Greetings, I'm Dr. Sharing Jenny, and I'm going to cover some topics in embedded microcontrollers. The topics that will be covered will be one module and two subdivision. One is related with the microprocessor architecture and some basics of the architecture, and von Neumann, Harvard, RISC and CISC, and simple assembly language programming. And the second half of this module will be PIC microcontroller and the architecture along with the features what you find inside the PIC microcontroller. To start with, we'll see what is microprocessor and a microcontroller. Microprocessor is a programmable device which can take binary input and produces a binary output, and again it should be programmed accordingly. In the case of a microcontroller will have some memory internally in a single chip, something like random access memory as well as the read-only memory. And again, it will often have some peripheral devices internally. You may have something called as the timers, something for serial communication, and some modules for analog to digital conversion, and some module for pulse width modulation, and some which is called as input output ports where more devices can be connected. So all these will be inside a single chip. So you should understand this is similar to that of going into a mall and finding all what you need. So that is something like a microcontroller. And if you go to a shop, a vegetable shop, you'll get only vegetables, and if you go into a textile shop, you'll get some dresses. So that's something like a microprocessor. So microprocessor, if you want to go for an application, you need to connect more devices, but in a microcontroller everything will be inbuilt. So the difference you need to add. So the main difference, microprocessor is used for a general purpose, whereas a microcontroller is for a specific purpose. Why? You know the reason, because I said you earlier, the microprocessor is just a processor, and if you want to convert that into an application, or if you want to use a microprocessor for an application, you need to connect all the additional devices externally. Whereas in a microcontroller, whatever application you want to design, you can choose microcontrollers accordingly. Some microcontrollers will have an analog to digital converters, digital to analog converters, the pulse width modulators, and timers, serial communication. So whatever application you need and what are the components you need or require, accordingly a microcontroller can be chosen and you can design accordingly. So the microcontroller is preferred for an embedded application. As you can see, you have two diagrams, one to the left and one to the right. One is on the left is a microprocessor, one to the right is a microcontroller. You can see in the microprocessor diagram you have a microprocessor. Externally you have input output devices and a memory is externally connected. So this should be programmed, the processor should be programmed accordingly, and from the input device it may fetch, or from the memory the instructions are fetched, and based on the input requirement it can produce the output after the execution. Whereas in the case of a microcontroller, you can see you have a CPU, you have some interrupt control devices, you may have a RAM, read-only memory, timer, serial communication, ADC, pulse width modulators. All these what I've given you is inside a single chip. That's the main important. Whereas in case of a microprocessor, what is given in the gray box is inside the chip. And to make you understand clearly, again I'm reiterating what I'm given here. CPU on a single chip. What do you find inside a microprocessor? So CPU on a single chip, it needs some memory, input output ports, and all other external devices and peripherals. And it's used for a general purpose system like PCs and calculators. Examples are 8085 processor and 8086 processor. Whereas a microcontroller, it's a CPU, a memory, and input output ports, peripherals, all inside a single chip, one IC, and it is used for a specific application. It should be for a consume low power, because you know that embedded application needs to have a low power. And examples are 8051, PIC, ARM, Cortex M4. And coming to the evolution, you have first generation, second generation, fifth generation, and it goes on. You can see something like word size. You have 4-bit, 8-bit, 16-bit, 32-bit and 64 bits. What do you mean by that? It means that the processor which comes under the first generation, it can process 4 bits at a time. For example, if you want to perform addition of 4 bits of data, first generation can do. And if you want to add 8 bits of data or subtract 8 bits of data, a second generation microprocessor can do. And you can ask me why the 64-bit processor or a 32-bit processor cannot do 8-bit operation. Yes, you can do. So, and again remember, 32-bit processor, it's meant for 32-bit processor. So if you want to perform 8-bit addition, it's waste. But the reverse is true. An 8-bit processor can do a 32-bit application. How? The 32-bit has to be divided into 8 bits each. That is 4 times the operation has to be done, replicated. It means that the operation will be little complex and it will take much time when you do the 32-bit operation in an 8-bit processor. The reverse is compatible, whereas this way it's very waste because you're wasting that much of bits and the time is also getting wasted. And some examples are given here, and you can see a picture on the right top with the evolution. You can see this is with the up to 2023 it's given, Intel 4004 up to Intel Core. And before going into the architecture, you should understand the difference between a von Neumann architecture and a Harvard. Von Neumann architecture, the diagram below, you can see a CPU and a memory. And the memory inside a single memory, one part will act as a flash and one part will act as a RAM. That means that you have data as well as instruction inside a single memory. You should understand that whenever we give data, the processor should be able to read the data, as well as after execution it should write into the memory. It means that it should be something like a RAM. And again you will have some memory, some instruction to make the CPU to run. So that it's fixed. So that can be written inside the read-only memory. So to make it simple, I can say that RAM is otherwise called as a data memory. Read-only memory is otherwise called as a code memory or the instruction memory. It means that the read-only memory, the data inside or the instruction inside the read-only memory is fixed. Whereas the data inside the RAM can be read and can be written into. So von Neumann architecture, you have a single memory for both for the data as well as for the instruction. So it's simple, but it will be taking much time. You just imagine you have only a single bureau for everyone. So everyone has to keep the data, keep the dress inside the single bureau, and you have to get all the dresses. So that takes time. And again, if I just imagine I have 2 bureaus and for 2 people, so you can get the dresses and easily you can go. So it's going to be faster. So parallel accessing can be done, right? So you can see the Harvard architecture, you have 2 memories, the dual memory, one for the instruction, one for the data. So where the instruction will be stored, it will be stored inside the flash memory. Where the data will be stored, it will be inside the RAM. And you should understand the pointers also will differ. So you may have pointers to fetch the data and to fetch the point to the address. So again I'm saying von Neumann, you have single memory both for the instruction and data. Harvard, you have 2 memory or 2 separate memory, one for the instruction and one for the data. Instruction memory, you call it as a read-only memory or a flash memory. Data memory, you call it as a. Thank you.